Okay. Factoring polynomials, we're going to start with polynomial of degree 2, which is a quadratic function. Okay. So I want to kind of start off really slow here, and you might be saying, Mr. Travis, I know this. Yes, you do. You should. But I want to make sure that you're very aware of the term called identity. We're going to need to remember and kind of work on identities a lot, so they're second nature in your head in order to start factoring, because factoring a polynomial of degree 2 is easy. Even factoring a polynomial of degree 3, that's somewhat easy as well. Until we get to 4, 5, and 6, that it becomes a little bit of an issue, right? So when we have the difference of squares, you've done this last year, you've done this year with me, the identity is a squared minus b squared equals the quantity of a minus b times the quantity of a plus b, okay? The minus and the plus, that's the reason that there's no 2ab in the middle here, because they cancel out, okay? So that's an easy way to determine how to factor difference of squares. Remember that. So do I have an example? I do. Okay. So again, here's the identity. Example 1. We're going to factor and solve x squared minus 81. Well, I know that you know it's x and 9, and it's a minus and it's a plus. But one thing to remember is you can rewrite 81 as 9 squared. That's something that you're going to have to want to do, not so much with quadratics, but when we get to degree 3. So this can be rewritten as x squared minus 9 squared, and then we factor using the identity as it's x and a 9, minus and a plus, okay? Or plus and a minus, whatever you feel, okay? And then with solving it, it's 9 and negative 9, moving forward. So there is no such identity when it's a squared plus b squared, only when it's a minus sign, as in the term difference of squares. There's no such thing as the sum of squares, which is that. Now, even though there's no identity for that, there is an actual methodology of solving for it, because a squared plus b squared yields imaginary solutions. So we could write this as the quantity of a plus bi times the quantity of a minus bi. Okay, and that's how that would break down if I were to factor that even further. Now, right now, I want to stay far closer into the realm of real numbers, and I want to stay away from the complex imaginaries. So let's keep going. Multiplicity, super important term. Multiplicity is basically when a polynomial has factors that repeat, okay? In quadratics, multiplicity can only be a maximum of 2, obviously, because there's only 2 roots, meaning 2 is the highest exponent or the highest, that. What? Oh, goodness, okay. Example 1, x squared plus 8x plus 16. When we factor this quadratic, we get the quantity of x plus 4 times x plus 4, or x plus 4 squared. That exponent right there is the indicator of multiplicity. There's only one answer. But the fundamental theorem of algebra says that there are 2 roots here. There are 2 roots. It just happens to be the same number twice. The multiplicity here specifically states that it is the factor of x plus 4 with multiplicity of 2, meaning it happens twice, okay? Now, other factors, other polynomials we talk about will have multiplicity of 3. Most will have multiplicity of 1, right? It only happened once. But it's going to be a really easy way for us to start factoring and solving higher level, higher exponent polynomials, okay? So even though the solution is only -4, it has a multiplicity of 2. Now, I'm going to go into this, but I don't know if it's on the next slide. Oh, it is. Okay, perfect. Okay. So what does multiplicity look like? It looks like greatness, okay? And here's why. So this only works with perfect square trinomials that are quadratics, okay? And the reason for that is because there's only 1 root that you're able to see, but there's actually 2, because the fundamental theorem of algebra says there is 2. But you're saying, because this is obviously here, right? Well, Mr. Dramus, there's only 1 root. Yes and no. The multiplicity of 2, because the multiplicity is even, says that the function is going to appear exactly like it does here. It's going to touch the x-axis. It will actually have a point of tangency here. It will actually connect. And then it will change direction. That is the indicator of 2 roots, even though specifically it only touches it once. All even multiplicities will do this. It will touch the x-axis, and then it will reverse pattern. Now, if it had a multiplicity that was odd, 1 or 3 or 5 or 7, it'll actually cross the x-axis, and that will be always the case, okay? So we'll talk about like linear functions and cubics and things like that later on. But basically, I want you to know what multiplicity looks like. Multiplicity is good when you have to sketch a function that you're not able to solve all of the factors for, because some might be irrational that are difficult to do, or some might be even imaginary. Okay. So multiplicity and the fundamental theorem of algebra. So what does it mean in terms of each other? Like, how are they linked? So we're going to have a discussion about this in the next coming days. Why does it say, the fundamental theorem of algebra, why does it say there are 2 roots here when there only appears to be 1? Okay, so that's something that we're going to talk about. One thing that I would like to throw out there is it really depends on what the behavior is of that function at the axis, meaning the point of tangency or where they connect. Really what's happening here? We know that a linear function will just cross it once and be done with it. And that's easy. It's got multiplicity of 1, it's only 1 root, period, end of story. But here it's a little bit different because it appears to kind of hang out here for a while. So I want you to kind of consider that as we talk about cubics, 4th root, 5th root, things like that. Because the function is going to appear to kind of hang out a lot longer around the axis than lower polynomial as well. All right? So I want you to think about that as we move forward. See you later. Bye-bye. Wow, 6 minutes. Goodness gracious. Okay.